Today we have to show that this condition that we found on the change of variables so that they are a canonical transformation actually have the structure of a mathematical group. Okay, so they have to have a neutral. So the neutral is the identity transformation. The identity transformation is canonical. And with lambda equals 1. So that's the case in which lambda equals 1. And it's obvious because the identity transformation is the one in which the change of variables. Remember that M is the Jacobian of the change of variables. So if the transformation is the identity, then the Jacobian matrix is nothing but the identity, and obviously the identity times identity transpose, this equals J. Okay, so that's that. So that's the first property. Let's put it like this. Okay. Now, second property. Second property is that the inverse of a canonical transformation is also a canonical transformation. All right. So that means that m minus 1 times j times m minus 1 transpose, this will have to be some valence times j. Okay. So let's see what this valence is and that this condition is fulfilled. In order to do that, so what we know is that M is a canonical transformation. So M is canonical transformation, which means that Mj means that Mj M transpose, this is lambda j. So if this is true, what happens here? So all we do is just we write M minus 1 j M minus 1 transpose, and we write this thing like this. So M minus 1 is M minus 1, J is J, and this is the same as M transpose minus 1, obviously. Minus 1 and transpose commute. So this is the same as, now I can put J minus 1. Remember that J minus 1 is minus J, right? J minus 1 is minus J, is one of the properties of this matrix. So this is minus M minus 1, J minus 1, M transpose minus 1. And now this is minus M transpose J M, right? M transpose MJ. Like this, whole thing minus 1. But this is minus, and if M is a canonical transformation, then this condition here is true. So then this is minus lambda J minus 1. Which is nothing but, minus lambda minus 1 j minus 1, which is nothing but, 1 over lambda times j, because j minus 1 is again minus j. So what we find is that this equals that. So that means that the valence of the inverse transformation is the inverse of the valence. This is something this simple, okay? So indeed, the inverse of a canonical transformation is transformation. So we have the neuter, we have the inverse of a canonical transformation is also canonical, so there is an inverse. 3, we have closure here, closure, which means that M1 times M2 is also canonical if M1 and 2 are canonical transformations. Okay, so let's do that. So M1, M2 times J, M1, M2 transpose. So this is the same as M1, M2 times J, M1, M2. Wait a minute, what am I doing here? This is not right. Sorry, so this is M1, M2 times J, and here M2, M1. This is right. Okay, but now M2 is a canonical transformation by hypothesis, so this is going to be a certain valence, let's call it lambda 2, times J. So then this is lambda 2, M1, J, and here transpose and transpose. And M2 transpose, I'm sorry, this I already did. So M1 transpose, like this. But M1 is also a canonical transformation, so this is lambda 1 times J. So that means that this is lambda 2 times lambda 1 times J. Okay, so that means that, you know, the valence of the product of two canonical transformations is just the product of the two valences. Okay, good. And now the fourth property is associativity. Associativity. But this is completely automatic because it just says that M1, M2 times M3 is the same as M1 times M2 times M3, which is always true, which is true for matrices, right? So the matrix multiplication, you know, fulfills this property. So now we have the four properties, you know, of a mathematical group. So that means the canonical transformations form a group. Any questions so far?
No.
Okay, so now we're going to introduce the concept of Poisson brackets. And the Poisson brackets are going to be very important because they are invariant under canonical transformations. And finding something that doesn't change always simplifies your life, right? So let's go by Poisson brackets. Poisson brackets. So what's the definition of a Poisson bracket? So the Poisson bracket of two functions one is going to be f of a bunch of q's, a bunch of p's, and time, and the other one is going to be another function of the same q's and p's and time with respect to the canonical variables Q and P. So the Poisson bracket is always, you know, with respect to some variables, okay, is defined as follows. So the Poisson bracket of F and G with respect to Q and P is the sum from J equals 1 up to N, all the variables of partial of F with respect to Qj, partial of G with respect to Pj, minus partial of F with respect to Pj. I'm going to define it like this. Let me just do it like this. Minus partial of G with respect to Qj, partial of F with respect to Pj. Okay, so in a condensed notation, we could write this thing as partial of F with respect to Q, partial of G with respect to P, minus partial of G with respect to Q, partial of F with respect to P. Okay, so that's a definition. And notice, if you write it like this, notice that this has the structure of something that looks very much like the commutator. The commutator, defining as the commutator, you know, something that first puts the two variables in this order minus the inverse of the orientation of the two variables, the inverse of the ordering of the two variables, right? So it's fg minus gf. And you do something to all these combinations. You do something to fg and you do something to gf, but the important thing is that it's fg minus gf. It looks like a commutator. So this is already smelling like the thing that you guys already know, which is that Poisson brackets are going to be related to commutators of the corresponding operators when you quantize the theory. Okay, so this is not a coincidence. Mathematically, you already see that the properties of the Poisson brackets, just because of what the definition is going to be very similar to the properties of the commutator of two things. Okay, now, given this definition, it's immediate to check that, you know, the Poisson bracket of Qi with Pj with respect to Q's and P's. So it's always necessary to specify this. Of course, this is going to be delta ij, right? It's going to be 1 if Q and P are the same canonically conjugate pair, and 0 if they are different, okay? And also Qi with Qj equals Pi with Pj equals 0. Okay, this is always 0. All right, so now we have defined the Poisson brackets. Now we can see other properties which are important, are the following. If I compute the Poisson bracket of all the Q's with f, then this is nothing but the derivative of f with respect to all the p's. Okay, now in components, this is Qi f equals partial of f with respect to pi. So it should be clear this vector notation what it means. Okay, and the other one is that if I take the Poisson bracket of p and f, a certain function, then this is nothing but the derivative of f minus q with a minus sign. Okay, again, so this is pi with f equals minus partial of f with respect to qi. Second property, which is a consequence of this, says that imagine that I want to take the derivative of a function, total derivative of a function with respect to time. Function which is going to depend on q, p, and maybe also explicitly on time. Okay, so the chain rule says that this is the derivative of f with respect to q times the derivative of q with respect to time, which is what we call q dot, plus the derivative of f with respect to p times the derivative of p with respect to time, and finally the explicit time dependence. That's the chain rule. Okay, now q dot is the derivative of h with respect to p, and p dot is minus the derivative of h with respect to q. So in other words, this is nothing but, you know, derivative of f with respect to q, h with respect to p, minus derivative of f with respect to p, derivative of h with respect to q, plus the explicit time dependence. So the derivative of f with respect to t is nothing but, you know, the Poisson bracket of f with the Hamiltonian plus the explicit time dependence of this function t, right? Which this is known in the mostly in the quantum theory. It is known as a famous theorem, right? Even though, as you can see, is nothing but, you know, direct consequence of the properties of Poisson brackets. So what is this theorem, this famous theorem that I'm talking about in the quantum theory? There's a famous theorem that, you know, is essentially this thing, except that, you know, except of talking about Poisson brackets, it talks about commutators of the corresponding operators. F is an operator, H is a Hamiltonian, an operator, and then this is a theorem.
Schrödinger von Neumann equation?
I don't think so. Maybe now it's a question of name. I don't know this theorem by that name.
Ehrenfest?
Ehrenfest, yes. This is the theorem of Ehrenfest. Right. In the quantum theory, this is presented as the theorem of Ehrenfest. But as you can see, it's just a direct consequence of the properties of Poisson brackets. And in particular, we can now see one of the properties that we already saw in a different way, which is what happens if we just take the derivative of the Hamiltonian with respect to time. Of course, this is going to be the Poisson bracket of the Hamiltonian with itself, plus the explicit time derivative of the Hamiltonian. But this is 0, clearly, because it cancels out exactly. So that means that the total derivative of the Hamiltonian equals its explicit derivative of the Hamiltonian. So if the Hamiltonian does not depend explicitly on time, then H is constant. This we already saw, and now we can already see it also coming from the properties of the Poisson brackets. Okay, now the Poisson brackets can also be used, you know, to write Hamilton's equations. So Hamilton's equations can also be written in terms of the Poisson brackets. And Q dot, which is a function which depends only on time, using the same derivation as before, is nothing but the Poisson bracket itself of Q with H. There is no explicit time dependence because that's all there is. The time dependence of Q is given by H. Just go back to the derivation I had, and that's the only piece that we have. And P dot is also the Poisson bracket of P with H. So that's how the equations of motion look like in terms of Poisson brackets. Now, we introduced also the symplectic notation, right, which was a condensed and compact notation, you know, in which we group together Q's and P's. Okay, so we can also use it in symplectic notation. We can also define the Poisson bracket. So F and G with respect to Q and P is partial of F with respect to Q, partial of G with respect to P. And now we can put 0, 1, minus 1, 0. And here the same thing, partial of G now with respect to Q, partial of G with respect to P. Okay, so this matrix is 2n by 2n, and these are n by n unit matrices. Okay, now this in symplectic notation, remember this was partial of F with respect to eta, and this is partial of G with respect to eta. Eta is a vector that, you know, contains Q's and P's altogether. So this can be written as partial of F with respect to eta transpose, because it's a row, times J, this is our famous matrix J, times partial of G with respect to eta. Okay? Now, in components, this is obviously partial of F with respect to eta A, J A B, partial of G with respect to eta B. Agreed so far?
Okay, yes.
Good. Now, the previous, I was going to say the previous commutators. You see, I'm already biased with this. Now, the previous Poisson brackets of Q with Q, Q with P, and all that, now can also be written in condensed notation as eta A, eta B, written the Poisson brackets with respect to, eta itself is actually J. Okay, so this sometimes is written JAB. This is sometimes written as eta with eta with respect to eta equals the matrix J. Okay, so this is what it means. Huh? So you have to be careful with the indices here. Huh? I mean, eta with eta means eta A with eta B for all A and B. Of course, eta A with eta A is going to be 0, but eta A with eta B is not 0. So this is what it means. Okay, more things is that if you compute the Poisson bracket of eta with a function with respect to eta, then respect to eta, if you wish, like this, then this is nothing but J times the derivative of f with respect to eta. Okay, so this is in condensed notation, what we obtained before. And again, this in components is eta A with f with respect to eta equals JAB partial of f with respect to eta B. And finally, the equations of motion, right? The equations of motion are eta dot equals the Poisson bracket of eta with h with respect to eta. Okay, and this is, so let me just follow the same notation, and this means that eta dot A is the Poisson bracket of eta A with h with respect to eta. So those are the equations of motion. Equations of motion. Good. So these are sort of like dynamical properties of the Poisson brackets. In particular, the last one is completely dynamical. It gives you the dynamical equations of motion. But there are some properties of the Poisson bracket. Algebraic properties of the Poisson brackets. First, antisymmetry. Antisymmetry. So that means that the Poisson bracket of A and B equals minus the Poisson bracket of B and A, directly from the definition. And as a consequence of this, the Poisson bracket of A with A vanishes. Second property, linearity. So that means that if I have a linear combination AA plus BB times C, this is A times AC plus B times BC, where A and B are numbers. Okay? Third property. The Poisson bracket of AB with another function C is A times B. Sorry. A times B Poisson bracket with C plus Poisson bracket of A and C with B. Okay, and if you keep this ordering exactly the same way I've written it, these properties are exactly the same for commutators, as you know, from quantum mechanics, right? And the last one is what is called Jacobi's identity. Jacobi's identity says that if you take the Poisson bracket of A with the Poisson bracket of B and C, then plus cyclic permutations, this thing vanishes. So the cyclic permutations means you push B to the left, then C gets pushed to the left one step, A goes pushed all the way to the other side, and you keep going. Now it's C that is pushed to the left, A is pushed to the left one position, and then it's B, the one that goes all the way around, and then the sum of these three things is identically 0. It vanishes identically. Okay, so those are algebraic properties of the Poisson brackets, and as you know, these properties are shared by the corresponding commutators in quantum theory. And now it comes I would say the most important property of the Poisson brackets, which is the Poisson brackets are invariant up to the valence. So that means that for a valence equals 1 under canonical transformations. That means a transformation is canonical if and only if all the Poisson brackets are invariant. Okay, so this is important. If and only if. So now we have another way. We had before a way to check whether a change of variables was a canonical transformation by verifying whether, you know, M, J, M transpose was lambda J, right? Whether this was true, was part of, was an element of the symplectic group, right? Now we have another way to check this thing, which is the Poisson brackets. And we see whether the Poisson brackets of all the quantities in one variable or in another variable, in the old variable, in the new variable, if they are invariant, then this is a canonical transformation. Okay, so let's check this thing. So let's see. So let's start. Okay, so we take two functions, f and g, and we compute the Poisson bracket with respect to some all variables eta. So that we said is partial of f with respect to eta transpose j partial of g with respect to eta. So that's a Poisson bracket in terms of the all variables, okay? But now we make a change of variables from eta to eta prime, which is a function of eta, right? And that means, so this is the change of variables that we want to know whether it is canonical or not. Okay, so that means that f is actually a function of the new variables, which is a function of the old variables. So that would be the change of variables for f. And g the same. G is also a function of the old variables through the new variables. Okay, so that would be the function as a function of the old variables. And so we want to know whether, you know, the Poisson brackets are the same with respect to eta or with respect to eta prime. So that's the question, right? So is the Poisson brackets of f and g with respect to eta the same as the Poisson brackets of f and g with respect to eta prime? Yes or no? Okay, so let's try to see this. Okay, so what is partial of f with respect to eta? I. Remember that this is a function of eta through the eta prime, so the change of variables. So this is the sum from j equals 1 up to 2n of the partial of f with respect to eta prime j, derivative of eta prime j with respect to eta I. Okay, so that's the chain rule. And this is the sum from j equals 1 up to 2n of partial of f with respect to eta prime j. And this is our old matrix mji. So this is mji. And so this equation says that the partial of f with respect to eta is m transpose. Remember that Now, this is M transpose partial of F with respect to eta prime element I. You agree? Because you see, if I want to put, this M, before the derivative, I have to interchange J and I, because otherwise I'm not multiplying row times column as I'm supposed to in a multiplication of a matrix times a vector, right? So as I'm saying, if I put this M, before, and I want to write this thing as a multiplication of a matrix times a vector, I have to interchange the indices to really make the multiplication of a matrix times a vector. So that means that I have to transpose it. Okay, so this is partial of F with respect to eta prime. Okay, so this is all I need, because now I compute F and G with respect to eta. And this is, given the definition of the Poisson bracket. Remember that this was partial of F with respect to eta transpose J partial of G with respect to eta. So then I use the previous calculation in terms of M, and therefore this is M transpose partial of F with respect to eta prime, whole thing transpose, right? Whole thing transpose times J times partial of G with respect to eta prime, obviously also partial of G with respect to eta is going to be M transpose partial of G with respect to eta prime. So that's what I write here now. So that is M transpose partial of G with respect to eta prime. Okay, and this is the same as partial of F with respect to eta prime transpose. M transpose is M, J M transpose partial of G with respect to eta prime. Okay, so that's what I find. Of course, this has to be this. And in terms of the prime variables, this would have to be, partial of F with respect to eta prime transpose MJ M transpose partial of G with respect to eta prime, J partial of G with respect to eta prime. This is if F and G with respect to eta equals F and G with respect to eta prime, right? Because then this would have to be this, and this is precisely F and G with respect to eta prime. Now, if this thing here, if this is J, okay, then this is true. If this is J, this is equals that, and then it's the same. So that means that if the if the transformation is canonical, then the Poisson bracket equals the same in the old as in the new variables. Okay, if it is lambda J, then there is a lambda here. So that's why. The statement is that the Poisson brackets are invariant up to lambda. So that's only for lambda equals 1. If lambda is not 1, then lambda multiplies the new transformation, the new Poisson bracket. So let's put a lambda here. In general, there is a lambda. So that's one thing. But then the other thing is that if the Poisson brackets are invariant, if this thing equals that thing, for all cases, for all F and G, then the matrix in the middle has to equals J, right? So that's why the whole thing is if and only if. Okay, so I repeat, if the transformation is canonical, then this thing equals J for lambda equals 1, and then this equals the same as that, and therefore the Poisson bracket is invariant. And reversely, okay? If the Poisson bracket is invariant, so this equals that, that means that this equals that, For all, now you need for all F and G, then the matrix in the middle has to be the same. So that also means that MJM transpose has to be J up to lambda. Okay, so that proves the result. Any questions or comments? Was this thing clear, or should I repeat something?
It's clear.
I couldn't hear.
It's clear. It's clear.
Okay, good. So, so that gives you, you know, an easy way to check, another alternative way to check whether a transformation is canonical or not. Just take Q's, the old Q's with respect to the new variables, or the new variables with respect to the old variables, and the Poisson brackets have to be the same. So Qi and Qj has to be 0, Qi and Pj has to be delta ij when you compute this thing in terms of some new variables after a change of variables. Okay?
Okay.
Now, the last property of Poisson brackets that we're going to discuss is what is called Jacobi Poisson theorem. And this theorem says the following: if f and g are two integrals of, so I'm going to change the wording. So I'm going to call them are two constants of motion, like for instance the energy or the angular momentum when the system is rotational invariant. Okay, so if f and g are two constants of motion, then the Poisson bracket of f and g is also a constant of motion. Okay, so this is nice, although it is less nice than it actually is. Because it sounds nice because it says, well, I mean, look, you find two constants of motion, and then just by computing, you know, Poisson brackets, you can find another constant of motion. So that sounds like, you know, like a little machine. You just crank up the machine, you know, you turn the handle more and more and more, and you find more and more constants of motion. Well, I mean, there has to be a little catch, right? This cannot be true, you know, in general, because we know that when the system, for instance, is given by, say, think of a standard Lagrangian or a standard Hamiltonian, which is the typical kinetic energy, P squared over 2m plus a potential B of R, even if it is central, okay? Well, you know that energy is going to be conserved, angular momentum is going to be conserved, the linear momentum is also going to be conserved if the particle doesn't have any external forces acting on it. All this, you have immediately, you know, three constants of motion, okay? Say energy, linear momentum, and angular momentum. But there are no more. So if you compute, you know, Poisson brackets with two of them, you cannot find a third one for free. There is no more. So that means that in these cases, the Poisson brackets have to vanish identically. So this theorem could be useful in some cases, but in the standard cases, the Poisson bracket of the old constants of motion is going to be a trivial identity. But nevertheless, for those cases in which it could be interesting, let us prove this theorem, okay? So proof of the theorem. Okay, so F is a constant of motion. What that means is that the derivative of F, total derivative with respect to time, is 0. But in the language of Poisson brackets, this is the Poisson bracket of f with the Hamiltonian plus the explicit time derivative, right? That we already saw. So this is true for f, and it's also true for g, because both are constants of motion. G with h plus partial of g with respect to time. Explicit time dependence, okay? So the theorem says that then, this is the thing that we would have to prove. Then the derivative with respect to time of the Poisson bracket of f and g, this, which as the total derivative of anything, is going to be the Poisson bracket of the thing with h plus, this is a plus, huh? Plus the explicit time derivative of that thing. So the theorem says, and this is the thing we have to prove, that the Poisson bracket of f and g with h plus the explicit time derivative of f and g is 0. This is what the theorem says. Is this true or not? Well, so let's prove it. Okay, so now take Jacobi identity. Jacobi's identity. Jacobi's identity says that the Poisson bracket of f and g plus all the cyclic permutations, so that means g with h and now f, and h with f and now g, this is identically 0, okay? Now, g and h is minus the derivative of g with respect to t. And this is because of equation 1, this equation, right? The Poisson bracket of g and h is minus the derivative of h with respect to t. And h and f is the derivative of f with respect to t. This is 2. So the equation 2 says that f and h is minus df dt, so h and f is plus df dt, okay, with the right signs. Okay, so that means that the 0 of the Jacobi identity is nothing but the Poisson bracket of f and g with h, so that's the first term. Now plus the derivative of f with respect to t times g minus the derivative of g with respect to t with f, yes, right, with f. So this has to be 0. Now, the only thing we need now is exercise. I'm going to leave it to you to prove that the derivative with respect to time of f and g equals derivative of f with g plus f derivative of g with t, which is another property that you may have seen written in terms of commutators instead of Poisson brackets, but is the same. The proof is the same because the algebra is the same. So I'm going to leave as an exercise this thing. And once you see this, then you're done, because 0 equals the Poisson bracket of f and g with h plus this, but this, here you have to write down this thing the other way. So just, exchange f and dg dt, and then it's exactly the same. And so plus derivative with respect to t of f and g. And this is exactly what we wanted to prove. So, okay, right? So this is true. Okay, so that tells you that, some things are very easy to prove written in the language of Poisson brackets. Like, for instance, this. Okay, Any questions or comments?
No.
Good. So now we're going to see that canonical transformations are something very, very, very close to Lie groups. Remember those who did, advanced mathematical methods last year? There was, like a month or something like this that was dedicated to Lie groups. The rotations are, a Lie group. Translations are a Lie group. There are many interesting groups in physics which are, Lie groups. Lie groups are basically transformations that form a group that depend continuously on a function. The case of rotations, for instance, you already know in quantum mechanics that a rotation is the exponential of, up to an I complex of, complex unit is exponential up to an I of the generator times an angle, right? So canonical transformations share lots of things with Lie groups. And for that, we're going to take another look at canonical transformations. And we're going to see how canonical transformations allow us to understand Nether's theorem in the language of Hamiltonian mechanics. The theorem was written in terms of Lagrangian mechanics and the action. So now we're going to see what Nether's theorem looks like in terms of the Hamiltonian. Okay, I don't think I'm going to be able to do all that today, but I'm going to just, get started with this. We're going to begin only, okay? So let's go back to the very beginning of canonical transformations, and let's imagine that we are given a general canonical transformation. So that, if you go back to the first, blackboard that we wrote down for canonical transformations, we saw that the differential of what we called the generating function is lambda p dq minus p prime dq prime minus lambda h minus h prime dt. Where here I'm just using for simplicity just one variable q and one variable p. If I have a bunch of them, I would have to sum here over all of them. So that's the thing. And this, because this is dq and this is dq prime, this suggests that it is advantageous to write the generating function as a function of these two variables, q and q prime, because that, that's the way the differential is, begins to be written. So just dq and dq prime here. So this is why we chose this one to begin with. Okay, but we can always, and we saw an example, we can always change variables and choose any other pair which is convenient and choose another pair. And in this case, we're going to change from q and q prime, and we're going to write it in terms of q and p prime. And the reason will be clear in what follows, okay? But let's imagine that we want to do this thing. How do we do this? How do we change variables? Well, it's much simpler than one would think. All you have to do is add the differential of something which depends on q's and p's, or q primes and p primes, not the derivatives of that. And so let's imagine that we add p prime and q prime to this generating function. Remember that the generating function appeared in the definition of a canonical transformation because the action is something that we can always add the differential of a function of p's and q's, right? That's how the generating function appeared on the very first slide in this subject. So now we add this term. we can also add freely this term. Nothing is going to change except that we're going to change variables. So if we do this, okay, we'll see what variables, you know, we have at the end. So it's going to be lambda p dq. That's what we have, minus p prime dq prime. Now we add the derivative, the differential of this thing. So we add this thing here. So this is dp prime q prime plus p prime dq prime, and then minus lambda h minus h prime dt. And so this differential is chosen so that this thing happens. There is a cancellation of this guy with that guy. And then what we have is lambda p dq plus q prime dp prime minus lambda h minus h prime dt. And now we already have these differentials explicitly. So that would be a function f of q, p prime now, and t. So we already changed variables in the new generating function. So I should put here a hat because this f is not this f, but in order not to have the hat all the time, I'm going to call this guy with a hat and this without it. Okay. So I already changed variables. So now this new generating function is such that df dq equals lambda p, but df dp prime equals q prime. Then df dt is minus lambda h minus h prime. So that's the same as in the previous case and the f hat. But this one has changed, of course, because I changed variables. Now, this f of q, p prime, and t is the right one, to define the identity canonical transformation. And what is the identity canonical transformation? Is the transformation that goes from q to q prime, which is the same q, and p that goes to p prime, which is the same p. So who is this f? Okay, so this is why we had to change variables to really find an f that does this stupid thing, this simple thing, you know, in a very easy way. So which is the f that does this thing? And I already tell you what, you know, the properties of the f is, the properties of the f are. And so therefore, I'm going to leave this thing as an exercise and I'm going to stop right here. So the next day, I'm going to tell you what the f is that does this trick. And then I'll take it from there. We'll see what consequences we can learn from this. Yeah? So we are going to start with a very simple, the simplest possible canonical transformation, which is it changes nothing. You go from q to q prime, which is exactly the same q, and from p to p prime, which is exactly the same p. And the interesting thing, of course, will not be this, but it will be what happens if we start making little changes with respect to this identity canonical transformation. All right, questions or comments, or otherwise we'll leave it at this point.
No questions.
Everything clear.
No questions, no comments?
No.
Oh,
Okay, so if that is the case, we're going to stop right here. So have a nice weekend. Okay, bye-bye.
Bye.
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 bye.